in data analysis or with analysts is that they sometimes imagine that we do statistics for the sake of statistics, or we analyze data for the sake of analysis. No, we analyze data to understand epidemiologic truths. So you can't be a good data analyst if you don't understand a little bit of epidemiologic reasoning. Now, we're not saying you should all go and get PhDs in epidemiology. No, that's not what we're saying. But what we're saying is that for you to really have insights into the analysis you're doing, there has to be some basic level of understanding of epidemiologic truth, what is bias, and all of those things. So we'll provide a very high-level overview of that so that we're all at least grounded to some degree in epidemiologic reasoning, which forms the basis for research. And then we'll then bridge those two areas together, the statistical reasoning and the epidemiologic reasoning. So principles of study design in statistical analysis. I'll cover some of those elements now. Now, for anything we observe in the universe, there are one of three explanatory mechanisms that explain every single thing we observe in the universe. If you see somebody successful or failing, if you see anything happening, there are one of three things that could explain anything we see around us in the world today. It could be the truth, it could be chance, or it could be bias, right? So in general, we always say that epidemiology is the study of truth, chance, and bias, because anything you observe can be explained by one of those three things. Now, obviously, the goal of research is to identify the truth. But as we say, the truth lies in the gutter, right? The truth doesn't just exist somewhere nice and clean. No, the truth lies in the gutter. And your goal as a researcher or your goal as the analyst is to extract that truth from the gutter and then to clean it so that it becomes clean and presentable. And remember, what you're cleaning is you are cleaning the influences of bias and the influences of chance so that the truth can stand by itself. That is why you do data analysis, to make sure that you separate truth from chance and bias so that what you're presenting is the whole truth. And that's why we do research. The word research literally means research, meaning to search over and over again. Well, why are we searching over and over? Well, it's because the truth lies in the gutter. And we can't just grab it, right? We have to search over and over. We have to search over and over to make sure that we have cleared truth from bias and chance. And that's why we do research, which means to search over and over. And the goal is to present the whole truth. Obviously, we want to avoid this one, the truth with holes. We want to present the whole truth. And the whole truth is one that has been cleared to be free of chance and free of bias. So that's why we have to understand these basics before we can understand why we do certain things in analysis. Otherwise, it just becomes head knowledge that doesn't move the needle from point A to point B. Now, when we talk about truth, in research, we call the truth validity, right? We introduced this concept yesterday, but I want to build on it today a little bit more. So truth means validity, right? And in general, there are two types of validity. We have internal validity, which is truth in the study, and external validity, which is truth in the real world. You can think of it as two people who love each other to death and they want to get married. Internal validity is saying these two people, do they agree to live with each other? Do they agree to be married, a married couple? That's what we're asking with internal validity. Now, if they agree, the next question is, does the extended family accept this union? Right? That's what external validity is saying. It's saying the external family, do they consider this union to be legitimate? So it should become immediately apparent that you can only talk about external validity in the presence of internal validity, because it doesn't make sense if the two individuals have refused to, they have not agreed to marry each other. The question of whether the family accepts that union becomes a trivial issue. Right? It's a moot point because they have to first agree that we want to be married to each other before we can talk about, oh, does the family agree or does the family disagree? So we can only explore external validity when we have determined that there is internal validity in the study. So what is internal validity? Well, internal validity, again, going back to a couple, is that they've said, okay, well, we think that we're a great couple because we don't have any lies between us. We don't have, everything is great. That's the same thing that happens in studies. Internal validity is when there are no lies in the study, between the relationship between the exposure and the outcome, right? There are no lies, there's no sketchy behavior, so there are no bias, essentially. Bias means error, systematic error. And so when we have determined that our study is free from bias, confounding bias, measurement bias, and selection bias, we then say that that study has internal validity. And then when we have proven that there's internal validity, then we can then ask, can we generalize findings to the broader population? Now, in the search of truth, because remember we said our goal as researchers is to find the truth, because the truth lies in the gutter, remember? If that's the only thing you take from the class today, that's awesome. The truth lies in the gutter, and your job as the analyst is to separate the truth from chance and bias. That's your job. And so sometimes you have to reposition yourself very clearly. I'm sure you've heard of the story of the 5 or 6 or 7 blindfolded men who were asked to touch an elephant and describe what they felt. And one said it's a fan, the other one said it's a spear, and so on and so forth. So the question is, which one of them is correct? Well, all of them are correct, actually. But then we can also ask, which one of them is wrong? And the answer is, all of them are wrong. So they're all correct and they're all wrong. They're all correct because what they felt and described was, in a sense, the reality of their experience. So the guy who said, oh, it's a snake, well, the trunk of the elephant feels like a snake. So you can't really fault them for being wrong. Now, the problem with all of them is that they're standing too close to the elephant, right? You can't stand that close to it and still be able to see the big picture of it. For you to be able to see the big picture of the whole elephant, you have to take a step back. You must move backwards from the elephant, right? And that's why we do the word regression, right? The word regress means to step back. I'm sure if you have some little nieces in school, sometimes you might ask them, geez, are you regressing or what? Because your performance seems to be getting worse and worse. So regress means to move backwards. And in data analysis, the reason why we do regression is because, well, we want to take a step backwards so that we can see the whole picture. We don't just want to see the trunk of the elephant. We don't want to just touch the tail or the tusk or whatever. We want to see the whole big picture. So in this case, in this illustration, the trunk and the legs and the tail, those are the individual data points. So when we're doing regression, we're not necessarily interested in the individual data points. We're not interested so much in what this guy on row number 2 had or what the guy on row number 7 said. No, we're interested in the bigger picture. So that is why we have to take a step back. And in doing so, of course, we sacrifice something, right? We can't see the final picture clearly, but we get the big picture of it in totality. And so the same thing applies to the expression, oh, so you can't see the forest for the trees. Well, literally, if you're standing by the tree, that means you can't see the whole forest. And for you to see the whole forest, you have to move backwards. You have to maybe get on a plane and move all the way back. And now you can see the whole forest. You can now appreciate that, well, there are some parts of the foliage that are green and some are orange and some have hues of purple. You can only see that pattern because you regressed, you moved backwards. Now, as you said earlier, that involves some sacrifice. You can't exactly say this individual tree looks this way because you are too far backwards to see the individual tree. But what you've sacrificed in the ability to see for the individual tree, you make up in the ability to see the whole pattern of the forest. The same thing applies to the earth. We all are literally standing on the earth right now, but maybe none of us has seen the earth in its full scope because we're too close to the earth, right? Only astronauts who have gone into space can see this with their eyes. And again, that same idea of regressing is emphasized here, because if you want to see the whole big pattern, then it's very important that we regress or we move backwards. So in a nutshell, that's why we do regression analysis. We do regression analysis because we are searching for the truth, the whole truth. Remember, not some of the truth. We want the whole truth, But the question is, how can we see the whole truth if we're standing so close to the data points? For us to see the whole truth, the whole big picture, we have to move backwards. We have to, in other words, regress. And that's why we do regression analysis. So the bottom line is that we need to understand how all of these things fit together so that when you're doing a particular procedure, it's not just that, oh, well, I read that people sometimes do this, or that you have to do this to publish a paper. Because it's based on solid epidemiological reasoning, and you know what you're doing. And so what regression analysis do is that they give us a model to explain reality. So on the screen here, you have an apple, but this is not an actual apple. This is a picture of an apple. Or put another way, this is a model of an apple. Now, one might wonder, why do we need a picture of an apple? Why don't you just give me the real apple? Well, it could be that you are in part of a world where there are no apples. And in all children's textbooks, we always say A for apple. Now, we can all agree that it would be quite bizarre to say A for apple, and we don't show a picture of an apple. How then is the child supposed to learn, even if they're in a place where there are no apples? And that's why we need models. The models allow us to give somebody who has never seen an apple a very simplified rendition of that apple so that they can see at least. Now, of course, they can't eat the apple, they can't smell the apple because it's not a real apple, right? It's just a model of an apple. So when we talk about models or modeling, that is what we're referring to. We're trying to create a picture of reality in a way that is very simple so that we can tell somebody who has never seen the actual data that, well, you see, this is the picture of this. This is what it looks like. Now, of course, you should know that this has limitations. This is not the real thing, but it gives you an idea of how the real thing looks like so that you can, at least, maybe hopefully when you see the real data, it makes sense to you. So models are a way for us to simplify reality in a very simple way. We say that all models are wrong. Obviously, that should be very apparent. This is not an apple. It's a very simplistic rendering of an apple, but it's not useless either. It helps to simplify reality to somebody who has never seen an apple. And it should also be immediately apparent as to why we need models. Why do we need a picture of an apple? Well, it's because we don't have an actual apple. Why do we need a model? It's because we don't have the actual data. We don't have the data to describe the phenomenon we're trying to describe. And so when we don't have the data, then we have to make do with the second best thing, which is a model of reality, simulation of reality. And so knowing this is important because I have observed this obsession with sophisticated methodology. People are obsessed with modeling. And sometimes it's like the individuals who want to do modeling so badly, they don't even understand why they're modeling or why they want to model. Maybe they just think it's cool to model. But my question is, have you actually tried getting the actual data? Have you explored all options? And then they might feel, oh, that's boring. Like, I want something more sophisticated. Well, that shows clearly you have no idea why we do things or why certain things are done, right? So let's not chase buzzwords or procedures for just because they're fancy, right? We need to understand why we do things in epidemiology or in statistical research. Now, we also must understand fully some of the variables we need for analysis, because a key part of analysis is to identify the variables you're going to need for your analysis. Yesterday, we introduced some of them, the types of variables like continuous or categorical. But in the context of your research, we're talking about this setup here. The first thing to do when you get your data set or you're asked to explore a research question is not to just dive into the data set. The first thing is to get a piece of paper, or you can open this page on your computer if you are the more digital type, and you think, right? AI can do a lot of things, but AI cannot think for you. And no automation can think for you. So we don't want to skip that part of research, the ideation part where we sit down and think that, okay, what is the exposure? What is the outcome? What are the confounders? What are covariates? And so on and so forth. That is the most important part of research, which we cannot skip. Now, let's explain what each of those things are in a very simple way so that all of us can be on the same page. So let's use this more simplified rendition of the previous page. This is exactly the same as this. So for the sophisticated, this is great, but let us just use this one to simplify what we mean so that when we start doing our hands-on session, we can be able to map the variables to what they mean. This is extremely important. This is the most important part of research, right? Sitting down at the very beginning to map what goes where, and so that we have a very clear understanding. Some of the questions people will ask will be questions like, oh, what variable should I use as my outcome? Or what are my confounders? Those kind of questions are not very ideal, because they show that you have skipped that ideation part of research. You simply grab the data sets and just, maybe somebody told you to do something, you never thought through it very carefully, right? So we, as much as possible, want to avoid such embarrassing questions. I mean, you may not view them as embarrassing, but when you ask questions that should be clear to you, especially at your level of research, then to the person who's listening, it becomes that they might start questioning your competence to even do the research in itself, right? So that's why we cannot emphasize enough that the most important part of research is for you to sit down and ideate at the very beginning. All right, so let's map these variables to this and be on the same page. So you first of all have to define, again, what we are, for clarity, we are assuming that you are looking at an analytical research question, right? Where you have an exposure and an outcome. So this does not assume you are doing a descriptive research. But let's go through it together. So you imagine here you have a tank with a lot of water, and your research question is, the main question you're interested in is this: how long does it take for all the water from here to drain down into this basin, right? That's what you're interested in. That's the only question of that matters to you. How long will it take for all the water here to drain into the basin through this pipe, the one in red? Here, this is your exposure. This is where you start from. So where you start from is called the exposure, right? So, and where you end is called the outcome. So if my research question is called, maybe I'm looking at the relationship between smoking and lung cancer, I'm starting with smoking and I'm ending with lung cancer. So my exposure is where I start, which is smoking. My outcome is where I end, which is lung cancer. So here, we're starting from the tank up here and we're ending in the basin. So this is our outcome. The green basin is our outcome. The tank is our exposure. This pathway is called the causal pathway, right? There are many ways that we could have gotten there, but that's the one we're interested in, the path from the exposure to the outcome by the causal pathway. Now, if there were no other pipes, life would be simple. We'll just grab a chair and, get a bottle of wine and just set our timer and see how long it takes. But here we have a problem. There are a lot of other pathways that the water is flowing that are not necessarily the causal pathway. Let's explore some of them. Now here we see this pipe here, the one in this brownish pipe. Again, it's taking water from here all the way to the same outcome, right? Now, if in reality it took 1 hour for water to flow from the tank to the basin in the absence of any other pipe, well, we might get a very different answer in the presence of this brownish pipe. We might conclude that the time it takes is 30 minutes because water is flowing here and water is also flowing here. Of course, that's going to alter the time, right? And that's the problem with confounders. A confounder is a variable that is associated with both the exposure and the outcome that does not lie on the causal pathway. So it's another pipe, it's another conduit through which information is flowing from the exposure to the outcome, but not through the causal pathway, right? And that's why they're very important. The goal in research is to exclude all confounders. So you must know what your confounders are at the very beginning. You must collect information on them, and you must include them in your analysis, right? When you don't include them, that's what we call unmeasured confounding, because they're not there in your analysis, so you didn't measure them. It doesn't matter whether they were in your questionnaire. As far as you include them in your analysis, you end up with unmeasured confounding. So this is a problem for us. So we want to make sure that we account for this. We want to eliminate this pipe. It's a problem for us, right? Because the question of interest is, how long does it take for water from this tank to end up in the basin? We're not interested in this pathway. So that's the problem number one that we have to identify. So now we've identified three variables that are important. The exposure variable, which is where we started. The outcome variable, which is where we ended. We've identified confounders, which are pipes through which information is flowing from the exposure to the outcome, but not through the causal pathway, right? Now, we also have a collinear variable. A collinear variable is a variable that looks a lot like the primary exposure, but it's not really doing anything. So think of this small pipe here. This pipe here is not really doing anything. We can remove this pipe and nothing is going to change. Nothing changes, really. So that's what a collinear variable is. It's a variable it's correlated with others. Collinear means co and linear. They're lying on the same line. So they're doing the same thing. It's like you have it's like, think of it as having a company where you have two employees that do the exact same thing. Now, the question is, why do you have the other person is redundant because they are doing the exact same thing that the other employee is doing, right? So what impact does that have? Well, now you, the employer, you're up there at night, instead of sleeping soundly, you are just anxious and saying, geez, am I going to make payroll this month? You have a lot of anxiety now because of this extra guy who is redundant. That is the exact same way that models behave. They become very anxious when there is a variable there that is not doing something unique, that is just a replica of another variable in some way, right? And that anxiety of a model is what we call is standard error. So the same way that you would behave in real life, that's how models also behave. And so that's why we don't want collinear variables, because they are just creating anxiety for the model. The model is wondering how it's going to make payroll, how it's going to cover explanatory power to all of those variables that are just here, not doing anything. So you want to make sure that you don't include collinear variables. It's your job as a researcher to identify which variables are collinear. It's also your job to identify which ones are confounders. And then here we have covariates. Covariates are variables that are associated with the outcome, but not necessarily with exposure. So remember that our research question was, how long does it take for water from the tank to get into the basin? But now we have water from the cloud, rainwater, getting into the basin. It's also a research question because now we have a source of variance. We have a source of water in the basin that is not from a tank. But our original question was, what time does it take for all the water in the tank to empty into the basin? So now we call it covariate because it's adding to the variation in the outcome, but it's not necessarily associated with the exposure. That's why it's called covariate, right? So you want to take note of covariate as well and adjust for them in your analysis. In other words, we want to adjust out the water that came from a cloud because that's not our interest. We're not interested in cloud water, but of course we acknowledge its existence. So we collect data on that and then adjust for it. We remove it out, and so that we focus on the question that matters, which is how long does it take for water from the tank to empty into the basin? Right. So those are some of the key ones. There are others here, but I'm not going to go into them for simplicity. But we need to collect information on all of those things and adjust for them in our analysis. Now, when you also design your study, you want to think of the study through the lens of PICO or PICOTS, or however you want to call it: population, intervention, comparison, outcome, time, and study design. Some of these things that match with this, for example, the intervention, the outcome, and all of that. Intervention is also called exposure. Every intervention is an exposure, but not every exposure is an intervention. Intervention means that we, the investigators, intervene. We gave a treatment to some group, but not to others, right? So interventional studies are also called experiments. Observational studies, we don't call them intervention, we call them exposures. So every intervention is an exposure, but not every exposure is an intervention. If my study is looking at the impact of, let's say, exposure to air pollution, I have people who are exposed or not exposed. That's just exposure. It's not intervention, because it wasn't as though I, the investigator, was the one who created pollution and assigned people to be exposed or non-exposed. All right, so and then it's also very important for us to define our inclusion and exclusion criteria very, very clearly. Sometimes researchers mix these terms up. They might say our inclusion criteria was being male, and then they will say our exclusion criteria was females. That does not make any sense. You're not making any sense. Inclusion, inclusion criteria is not just the reverse of exclusion criteria. If I put my arms around a group and say everybody in my embrace is part of my study, or everybody here meets the inclusion criteria, that means that everybody inside here, including the green checks and the question marks, they meet the inclusion criteria, while everybody outside here, right, they are ineligible because of not meeting the inclusion criteria. So that's clear. That's what inclusion criteria is. Exclusion criteria means that within the people that are defined by my embrace, I then look at some people and say, oh, well, you meet the inclusion criteria, but I have to remove you for whatever reason. That's what exclusion criteria refers to. There are individuals who otherwise meet the inclusion criteria, but have to be removed for whatever reason that you have defined. So these guys, for example, they will be removed by virtue of the exclusion criteria, even though they have met the inclusion criteria. So you have to define all of this very clearly in your analysis. And you have to create a statistical analysis plan. We cannot talk about analysts or training of analysts without talking about a SAP. So, most times you hear the word SAP or PSAP. SAP is statistical analysis plan. PSAP is protocol and statistical analysis plan. Sometimes they're together. The protocol refers to how the study will be conducted. The statistical analysis plan refers to how we're going to analyze data. So before you do anything, you need to have a plan. The plan should say, okay, what are the variables? What are my confounders? What are my exposure and outcome variables? How am I going to analyze them? What kind of analytical procedures will I perform? And of course, that is driven by the type of variable. And then how am I going to present the data? So that's what you need to do. You need to create table shells. If you're more old school, I'm a huge fan of table shells. Table shells are just empty tables that don't have anything. I always require my students to have the table shells for all the things they do. So that way it forces you to think about how will the analysis look like before you ever do the analysis. All right, so we're going to now take all of this and do it in practice and see how all of these things fit together in practice. So let's go back to our let's see, our projects. All right. So for those of you who are new, we're using the Kairos platform I saw some questions yesterday about, which app are we using? We're using the Kairos platform for the duration of this 4-day workshop. Kairos platform provides end-to-end support for everything that is research, from data collection to analysis and all. All right, so you can log in if you have an account, or sign up if you don't. I've already signed in, so I'm going to, sorry, let me switch this to light mode so that people can see clearly. So you can create an account here if you don't have, and then to sign up you can just click on there and fill the information, and then to sign in you can sign in with social media or with your username and password, as the case might be. All right, so let me go back to my account here. All right, so let's go to our project from yesterday. And today we're going to close this and start day number 2. So day 2. And we're going to call this statistical analysis planning and variable creation. All right. So let's go back to, let's make sure there's some things, everything that we have to complete on day 2 is actually completed. We need to create variables. I think we did some of this yesterday. Okay, the only one we have to make sure we do is working with dates. All right, well noted. So let's upload our data sets as we did yesterday. I think that was this data set here. All right, so now we have our data set there. Now, like we said yesterday, when you upload the data set, the first thing is not to jump into the analysis, but to make sure that you take a history, you inspect, and all of that. We're going to skip those steps because we covered those extensively yesterday. We'll just go into our research question. So in this case, our research question today for our session will be, what is the relationship between gum disease and diabetes? So let me create a document so that we can just type our ideation. Again, don't just jump into analysis without having some kind of ideation over what you're trying to do so that you get things right. So research question here is, what is the association between periodontitis, which is gum disease, and diabetes? All right. So what are some basic do's and don'ts? Whenever you're working with cross-sectional data, please try to use the words association. In epidemiology, we're quite strict with the words like effect. These are very, very strong words to us, right? We try to avoid them where we can. Effect, impact, obviously cause or causality, or anything that remotely suggests causality are things you want to avoid when you're using cross-sectional data, right? So try to use association. Association is like a two-way street. A is associated with B means that B is associated with A. A causes B is not the same as B causes A. So we want to make sure that we keep that very clear. So this is our research question. So let's go back to our screen. So let me go back to I'm going to be jumping a lot between this and this. All right. So let's map out these terms here: exposure, outcome, and all of us other confounders. For now, I'm just going to keep it to exposure, outcome, and confounders. Those are the most important three on this list. All right. Exposure, I have so many screens open, sorry. So our exposure is where we started, right? Our exposure here is gum disease.
Ross?
Yes.
Sorry, are you able to switch to light mode?
Okay, let me do that. Let me just log in. I like using a dark mode, but I understand that most people don't see that clearly. Let me. Am I using the wrong? Okay, let's see. All right, good. All right. So our research question is, what is the association between periodontitis and diabetes? When you come up with research questions as an analyst, the research questions shouldn't just be that you just slept and dreamt of something, right? There should be at least plausible. There should be some biologic plausibility, right? In this case, periodontitis, obviously, as it ends with the word tis, implies that it's an inflammatory disease. And as I will imagine, this is me, like maybe this is my first time with contact with this research question, like, and I'm thinking, oh geez, well, this is an inflammatory disease, and I know that other inflammatory diseases have some impact on insulin production, right? So my coming up with this research question is not just out of the blues. Maybe I've read the literature extensively and I've seen that there's a basis to ask that question. So just to say that your ideation of research question should be based in some some reality, right? It shouldn't just be some random idea that came to your head. And when you are framing your research question, remember we said the exposure is where we start, the outcome is where we end. That's exactly how you also should frame it. So it wouldn't be appropriate to say, in this case, what is the association between diabetes and periodontitis, right? Because my exposure is gum disease, that should come first. So the exposure is where we start, the outcome is where we end. So exposure is gum disease, and the outcome is diabetes. So we've mapped those two parts already now, exposure and outcome. Now, the next very important thing is confounders. Remember, a confounder is a variable that is associated with both the exposure and the outcome. This is our confounder, is associated with exposure and is associated with the outcome, and it does not lie on the causal pathway. If it lay on the causal pathway, then we will call it a mediator. So a mediator is a variable that is associated with the exposure because it started from here, and is associated with the outcome because it ended there. But a mediator, unlike a confounder, lies on the causal pathway. Or if we went back to here, you can see that this mediator pipe, the causal pathway started, and then boom, you see this pipe came from this causal pathway. The problem with this is that it's taking out water that was supposed to come out here. Some of that water is trickling into the mediator pipe. And that's why you want to make sure that you are aware of what mediators are, because the last thing you want to do is to include the mediator in your regression analysis. So we're interested in them, not to include them in our analysis, but to make sure that we don't include them, to make sure we exclude them. Imagine in this case here, we are looking at diabetes. We're looking at, for example, we're looking at, gum disease on one hand and diabetes on the other hand. And our thinking process is that you develop gum disease and then you develop some inflammatory response, maybe which is captured by increase in levels of cortisol in your body. So cortisol levels, and then this, or some cytokines, right, or whatever the mediators are, and then that is what results in diabetes. So this is, in our mind, the pathway that occurs. Imagine that somebody in all of their wisdom decides that they want to adjust for cortisol levels. That is horrible. That is a no. Because now you have this mediator variable that explains why gum disease causes diabetes or is associated with diabetes. And you are now removing that explanation away, right? That's the problem with when you adjust for a mediator, because here, all the water that was supposed to pass through this red pipe is now passing through the mediator pipe. It's like, why did you put the pipe? If your interest was to know how long it took for water to flow from the exposure to the outcome via this causal pathway, why in the world do you think it's a great idea for you to now adjust for the mediator? Makes no sense. So the moral of the story is, please do not adjust for mediator variables. And that's key. So confounders are associated with exposure and with the outcome, but do not lie on the causal pathway. So the question is, what are some variables that are associated with gum disease and with diabetes, but do not lie on the causal pathway? Well, we can immediately think of variables like demographics. For example, we can think of age. People who are older are more likely to have gum disease. People who are older are more likely to have diabetes, report diabetes, right? We can think of gender. We can think of some comorbidities, comorbid conditions. We can think of educational levels as a proxy for many, many things, or income levels. Because you also have to worry about what's in your data set. A variable like education could be a waste basket for many, many other explanatory things. Individuals, for example, who are educated may be more likely to be health conscious and to, take better care of their oral health, and also to eat better and have less likelihood of having diabetes. That's the explanation you want. These are the things that you want to be thinking about. when you talk to students or graduate students, one of the common mistakes they do is I'll ask them, so how did you determine that this variable is a confounder? And they will say, oh, well, I read it from the text, I read it from one paper. It's like, oh, that's great. But please don't just extract confounders from a literature. The most important tool, the most powerful tool to detect confounders is your brain, your common sense. Because the fact that the variable is a confounder in that guy's study does not mean that it's a confounder in your study, right? It's context specific because it depends on the population, it depends on a whole lot of other things. So it is not a great idea to just say, oh, well, I'll just go and see what other people did in their own studies and just replicate. That's just intellectual laziness, right? And we don't want to do that. So the most important thing is for you to sit down, get your notepad, and think and use your subject matter expertise to say, okay, I, as an expert in this field, I know that so and so are associated with so and so and with so and so. So this is very important, right? So this is what you want to do at the beginning. And then and only then can you then move on to create your table shells. All right. Now let's move into the data and let's see how that works out. Let's oh, sorry. I plan to go to the analysis now. Let's go to the analysis and let's load our data sets as we have. And let's now create the key variables we need and then get started. So again, as an analyst, your job is to think, right? It's not just to write code. The writing of the code or generating the results is the easy part. Anyone can do that. The biggest job you have is to think and say, what am I trying to get? What am I looking at? And why do I think that things might go that way? All right, so now we've uploaded our data sets, which is here. We just want to make sure that we create the variables that we need. So let's go to the glucose variable we had yesterday, and let's create the diabetes lab. So let's recode. So we said yesterday that individuals with glucose levels above 120, and I'm just using that number arbitrarily, by the way. So for demo purposes. So let's say 120 and above. Confirm. So we're going to edit the label and call this 0. So we're using the glucose level measured and saying individuals above 120, we're going to classify them as having diabetes, and those below that as not having. And so we're creating the binary variable 0 and 1. 0 means you don't have it, and 1 means you do have it. So this will be, let's edit the label to call this 1. And let's, again, yesterday we called this, I believe we called it diabetes from a lab. And let's proceed. All right, so we've created our first variable. We also had self-reported diabetes. So diabetes that was self-reported, yes or no. Let's also recode this to a binary variable 0 and 1. So we just need to edit the label for this. Let's call no 0. And let's call yes 1. So today we're going to use the visual method only because I don't like suffering. So we're going to call this diabetes self-report. Now let's create a variable that is either diabetes self-reported or lab. So either of those two. So we'll come to data processing, create composite variable using conditions. We're going to select our variables, which is this two. Let's make this bigger. So we're saying you are said to have any diabetes if you reported 1 here or 1 here. So we're going to just drag this here. And the relationship between them is or. So 1 here or 1 there. So move this here. And we're going to assign all the remaining observations into a separate category and exclude missing values. So let's just call this, let's edit the label to 1 and 0, binary to 1, and this is 0. And we're going to call this diabetes any. All right, so we've created that variable. So we have our exposure variable here, which is periodontitis. That was already existing in the data set, so I don't have to create it again. We have our outcome variable, which is the diabetes we have from a lab, from self-reports, and either of the two. Now let's create our confounders. So this is how you want to be going through the process, right? It's not just some arbitrary process you're going through. You're thinking, okay, I have first sat down and mapped out my DAG. Oh, by the way, that stuff we're creating, that's the fancy name people call DAGs, directed acyclic graphs, right? So in case you've been hearing of DAGs, that's what this means. You don't have to be fancy about it. You just need to know, what am I looking for? I'm looking for variables that are associated with the exposure and with the outcome and do not lie on the causal pathway. All right, so let's look at our confounders. We said things like comorbidities. And so we will have, I believe there's a variable called comorbidities. Medical condition, good. So binary 0 and 1. 0 meaning you don't have it, so we can leave it the way it is. The name is a bit too long, but that's fine. We can live with that. And then we can have also education. Education level is also here. Let's look at the categories. All right, we have, all right, less than high school, some college or more, high school or GED. So okay, that's fine. And then let's see also income. Income is also here. Let's look at the categories. All right, we have all those categories there. Now, one of our tasks for today was to also make sure that we capture working with dates. So let's just create a scenario that involves working with dates just to demonstrate how to work with dates. So imagine here that I have these variables here that have to do with dates. And our goal is to, let me search, I believe I have some date variable. So let's say you have two variables here, date of admission and date of discharge. And so your argument is that, well, obviously, how long you stay in hospital is a marker for how sick or unwell you are, and that might be associated with exposure or the outcome. That's the argument we're going with. But you need to create a new variable from these two. So a huge part of the work you're doing as an analyst is to somehow create variables you need to use, but which don't exist yet. So in this case, we need to use that variable, which is the duration of hospitalization. But what we have is not a duration. We have just date of admission and date of discharge. So we need to create a new variable from these two. So I'll just show you how to do on the chi-squares platform. You come to data processing, and you come to date transformations, and you select which one you want. There are three major operations there. One is date extraction. Date extraction says, select the variable you're interested in, let's say date of admission. The system automatically identifies the date format that you have. And then here it's like, what do you want to extract? You want to extract the year, the month, or the day. So it might be that I want to take that date variable and extract the year for each person. Maybe my analysis is maybe like a time series analysis, and I'm interested in the years, just the year. So in that case, I can just say, okay, extract year and call this, year and extract. So in that case, the system takes that information and see it has now extracted the data and generated years instead of just original dates. Original dates were not, if you compare the difference, these are discrete variables. The original variables were string, if you remember. right? So that's why data operations are very powerful. They allow us to be able to get or generate variables really, really fast in a way that does not introduce error into the operations. So that's one data operation there. The other one is, let's select our date calculation between two variables. So here you have two variables, date of admission, date of discharge, and you want to look at the difference between the two of them. So in that case, I'll select that. I'll select the first variable, which is date of, for example, admission, and the system automatically detects the format it's in, so you don't have to do it manually. And then the second date, the date of discharge, system automatically selects that. And now you can also preview the variables you've selected just to make sure that what you have selected is indeed is what you expect to see. So in this case, you have date of admission. This is a snapshot of the data set, just focusing on the two variables you selected. And then you select what you wish to, the time units for expressing them. So the difference between the two dates, do you want the difference to be in days or in months or in years, right? You can then select what you want, and that the system will calculate for you automatically. The same thing applies to fixed variable date interval. Here you have one variable, let's say dates. There's a homework for this so that you help you practice. And then you have a single variable that has a date, but you have a fixed date. Let's say you want to know how old is everybody from their date of birth up to this point, which is September 25th, 2025, right? So in this case, I'll select the date of interest, and I've selected the variable, and the system will then calculate it based on whatever I select here. Do I want the time period between the two dates to be expressed in years, in days, or in months? So that's how you can express that. And I just need to cover that since we indicated working with dates. All right. Now let's go back to our research question now. Having created our variables now, a very, very important thing for us to do is to create an analysis plan, right? We've mapped out our variables such that we know our exposure and outcomes and our confounders. But the question is, that still doesn't tell us how the data will be analyzed. Like, how are you going to analyze it? So as an analyst, you have to be very proficient at creating an analysis plan, a statistical analysis plan, and where you can say, okay, well, here I'm going to have table 1, we'll focus on this. In table 2, I'm going to look at descriptive analysis that looks at so and so, and that's what an analysis plan is. So let's create our analysis plan to explore the research question we have in mind now. You can do it manually if you want, but again, since I don't like to suffer, I'm just going to use the analysis wizard to help me create my own statistical analysis plan. Again, remember the statistical analysis wizard. The analysis wizard is for people who are not sure of what they're doing. If you don't like to suffer, if you're not sure of what you're doing, or if you don't know what you're doing at all, then well, the analysis wizard is for you, right? It's supposed to make sure that you generate correct inferences, even if knowledge is a barrier in your case. So I'm going to click on analysis wizard and go to analysis suggester. It will, again, to suggest an analysis. And once I approve that analysis, that becomes the analysis plan, right? Of course, I can modify its suggestions. That's why we didn't call it an analysis plan, because it's not a plan until I approve it. Until then, it's just a suggestion. So let's click on analysis suggestion, and let's select the variables that we care about. So here, the first one says choose the single most important outcome variable for your analysis and specify its type. And you see a button here that says show justification. The explanation here says that every study needs one main outcome, just like a ship can only have one captain. We try to be very, very simple with our terminology here at Chi-Squares. So we don't like big words. If you have several possible outcomes, choose the most important one as your primary outcome. The others can be listed as secondary outcomes. So you can only have one primary outcome in a study. You can have, that's why it's called primary. Every other one's a secondary. So how do you determine what the primary one is? Well, Your primary outcome should be one that best represents what your study is about. The one you would mention first if asked for a quick summary. Factors like the impact, the prevalence, the stakeholder interest, and data quality can guide your choice. So I may have a variable that was measured in the lab but has a lot of missing values. Well, maybe I shouldn't use it then, right? Because the data quality is a major issue that we want to consider for our main outcome. So, but in our case here, our main outcome here is diabetes in the lab, as measured in the lab. Because our research question is, what is the association between periodontal disease or gum disease and diabetes? And we want to put our best foot forward. If we have diabetes measured in the lab and diabetes that is self-reported, we obviously want to use the one that has less bias. And I'll go back to the slides here. Remember, we talked about internal validity right here. And we said that internal validity is the extent to which our study is free from bias. Remember that the truth lies in the gutter. The truth is found in the gutter. And our goal as researchers is to isolate the truth from chance and bias. Emphasis on bias now. We have different tools to help us achieve each of those objectives. That's why we use a p-value. The p-value's job is to correct for chance. The reason why we use regression analysis and all the sophisticated methodology here about, like, propensity score matching or G estimation or all of those things, all those fancy things are concerned with controlling for bias. Because again, truth chance bias explains everything we observe in the universe. So how do we control for the other two we don't want? That's why we develop all these methodologies in epidemiology to control for chance, which is why we have, again, p-values, and to control for bias, which is why we have regression and all these other methodologies, right? And so here, we want to make sure that all the sources of bias are identified and eliminated to the extent possible. And again, we're interested in measurement bias, confounding bias, and selection bias. The reason we came back to this screen was to spotlight measurement bias, which is also called information bias. That will occur when we have, for example, misclassification. We're interested in individuals. Do you have diabetes or do you not have diabetes? Those are the two binary states we're interested in. Well, we want the category of people who don't have diabetes to be only people who actually do not have diabetes. We want the category of people who have diabetes to be actually individuals who truly have diabetes, right? We don't want to mix some people in this group in the other group or in this group with the others. When we mix and match, that's what we call misclassification, right? We don't want misclassification because misclassification will end up causing us measurement bias. And so the choices of variables we include in our analysis are important because they influence the extent to which we shield the study from bias. That's why you have three shields here, right? The shields are here to protect your study from the impact of these biases. And so we have to make a decision. In this case here, okay, we have two variables. We have measurements in the lab and measurement by self-report. Which one should we use? The reason why we went through all the slides is so that you are empowered to think about those things when you're selecting variables. So at this moment, you should think and say, okay, well, I should be careful about measurement bias here, misclassification bias. So for that reason, I'm going to use this variable as my outcome, right? That's how you want to think about the whole process. Then here we have secondary outcomes. Our secondary outcomes here will be end diabetes as well as diabetes that is by self-report. So let's select that and let's so diabetes self-report. Sorry, my screen is a bit very massive, so things tend to hide on that. All right. So now we've selected our primary outcome and our secondary outcomes. If you want to see the justification or the explanation for the secondary outcomes, again, you can click the button here. So it says that it provides some explanation to you for why the secondary outcomes are needed. Here it says, we ask you to select at least one secondary outcome. Secondary outcomes add depth. They help check whether results are consistent and they strengthen your story. So remember that in epidemiology, we're very interested in consistency and coherence. Consistency means we do the same thing and we get the same results. You can't demonstrate consistency in one study. Consistency is demonstrated across studies, right? But what you can demonstrate, in your one study is to, demonstrate coherence. So other secondary outcomes help you to establish consistency with other studies. They also help you to establish coherence in your study. Coherence means that all roads are pointing towards Rome. If you have several indicators, the primary outcome is saying yes, and the secondary outcomes are also saying yes, maybe the answer is a yes, right? So when the results all point in the same direction, that's what we refer to as coherence, even though the constructs themselves are different. So you can read more for examples of outcomes that you could use as secondary outcomes. And so it says here that when these different measures point in the same direction, we call this coherence. It makes your findings more credible. All right, so we've selected our secondary outcomes now. Now, our main predictor or main exposure variable is periodontitis or gum disease, which I'm going to select. And now we have to select demographic variables or key covariates, right? So key covariates, again, these are variables, like we said earlier, that may be associated with the outcome, but not necessarily with the exposure. If you recall, our slide from here, right? Our cloud or rainwater is a covariate in this case because it's allowing water to fall into the basin, but it's not associated with the exposure. And so here you are being asked to supply variables that are demographic variables or those that are covariate. So here I'm going to select variables like comorbidity, okay, income, of course, which is a categorical variable. I'll select sex, I believe we have that variable here. I think we have age. I believe we have race as well. Education. Oh, there's a typo there. Education. Comorbidities. Oh, medical conditions. That's the name. Medical condition. All right, this is just a demo. This is not to make it exhaustive, but so select those variables and we can indicate the type of variables they are. They are categorical variables. So in this case, all I had to do was now, again, specify my outcome, primary outcomes, secondary outcomes, my main exposure predictor, and my demographic variables and covariates. And just click on suggest analysis. So now the platform will create an analysis plan for me. All right. So here it has said, okay, for your research paper, you're going to need, let's see, 4 tables, it says. Table 1 will be called characteristics of a study population. And these are the variables that you should have in it. You should have, these variables all in it. And it provides a justification for why that is needed. And it says you should have table 2. Table 2, it says, will be overall and stratified prevalence estimates of the selected outcomes among the study population. Again, it provides the justification for why it made that suggestion. Table 3, it says, will be regression analysis, adjusted odds ratios in the binary logistic regression to assess factors associated with the diabetes lab in the study population. And then table 4, it says, will be a sensitivity analysis using adjusted prevalence ratios. All right. Now, before we go on to run the analysis, let's come to this part here that says view variable selection diagnostics. We're interested in, are the variables we have selected actually confounders? Our research question is interested in measuring the relationship between periodontal disease or gum disease and diabetes. And we want to make sure that the variables we have selected are indeed confounders. So when we come here, we can view that the platform automatically does all of that for you in the background. So here we can click on confounding variables. So here it says that the following potential confounders demonstrated independent associations with both the exposure and the outcome at a specified significance threshold of p equals 0.2. Now, let's explain some things here. When we are setting thresholds for determining confounding, we generally do not use p 0.05. It is too small. We use a much bigger p-value, right? Traditionally, we use 0.2, but you can change that to whatever you want. You can change it to, there are options provided here, but we've set that the default, which is traditionally used. And again, remember, the confounder is a variable that is related to both the exposure and to the outcome, but does not lie on the causal pathway, right? So here, the platform has done the analysis in the background and has determined that these variables are indeed confounders of that relationship. If I want to look at the results or what it did, I can click on this button that says view results from bivariate analysis. That will show me the analysis that the platform did in the background to come to that conclusion. So remember that test for confounding is a two-part test. The first part of the test is this variable associated with the outcome independently? The second part is this variable associated with the exposure independently, right? And so here you have part one, test for association with the outcome. The platform takes all the variables that I have selected and tests them with the outcome, which is diabetes lab. And in each case, you have the results, the chi-square statistic, the degrees of freedom, and the p-value, right? So here we see a lot of variables are associated with, with the outcome at that p-value, 0.2 p-value threshold, right? So that's the first part of the test. How are these variables? Are they associated with the outcome? But then that's not all. The second part of the test must also include assessments for association with the exposure, which is what the platform does here too. So the second part of the test is this variable or are these variables associated with the exposure? And now this is the exposure variable. It takes each of these variables and runs a test for association. The platform knows the kind of test that needs to be run. It doesn't need you to tell it the kind of test that needs to be run. In this case, all the variables are categorical variables, and so it runs a chi-square test for all of them. It determines the kind of test. It knows the sample size, obviously, for the data set you've uploaded. So it determines whether a particular test needed is parametric or non-parametric and executes the test accordingly based on its recognition of a variable type. So in this way, your job as a researcher is then to look at this and say, okay, my variables that I have, I can see that, okay, these are confounders, and maybe the other ones are not so related, but I will still keep them because they're important, or I can choose to remove them because maybe they're not important to me. Those are decisions that you will have to take. Like I said, you can also change the p-value threshold. You can say, okay, instead of using a 0.2 threshold, I can choose to use a 0.1 threshold. And that may or may not, that changes the results here, right? In this case, the results are still the same, but the platform reevaluates the associations at that new threshold and then tells you. Of course, you can do this manually, but again, if you don't like to suffer, that is already done in the background for you. The same thing applies to collinearity. Remember, we said collinearity is a bad thing for us because it causes our models sleepless nights. It inflates the standard errors for the model. The variables just here is doing nothing really, right? So we need to be able to assess for collinearity in our research to make sure that we're not just including variables that are just reflections of each other. So when you click for collinearity, the platform takes those variables and also does a test for collinearity, and you can now see in the visualized form as well as in the table how the variables are correlated with each other. So here I can see that, race and education, it's not large at all. These are very, very small correlations. I can see age and medical condition, it's relative to the others, it looks large, but in the grand scheme of things, this is still low, right? So I don't have any problem with collinearity from all the variables I selected. And again, this is to protect you so that you don't just load up variables in your analysis that cause very, great deal of instability for your regression models. So now, if I want to run this analysis, if I'm satisfied with the suggestions provided, I can then proceed to run my analysis. So for example, table 1 here, characteristics of study population. If I'm interested in that, if I don't want to change anything here, all I need to do is click on run this analysis. And if I want to run it in the entire data set, I can, or I can select a subset. Here, I want to use the whole data set. So I can click on just estimate. All right, platform takes the data and has run the analysis. And all we can do now is review. If we're happy with the results, we can then push them to our data set, our manuscript, right? So we can push results to the manuscript. We can create a new manuscript if on the fly. Let's call this the relationship between periodontal disease and diabetes among US adults. So that's our project title. We have aims. We can type the aims ourselves, or we can ask AI to generate them for us. The platform does not use AI for anything that has to do with data, because that's too dangerous, obviously. We need to be 100% correct 100% of the time for anything that has to do with data. But for lower hanging things like aim suggestions, we use AI for those things. So it's going to take that context, and it has suggested some aims here. To examine the prevalence of periodontal disease, I like that. To explore the relationship between periodontal disease and diabetes, okay? And to examine risk factors. Well, that's not part of our aim. We're not looking at co-occurrence. All right, let me just select this one, and let's add those, and then let's start writing. So now we have our manuscript created. So let's push those results so now the tables we created, we've now pushed our results from the analysis to the manuscript. We can choose to either go and view the document, or we can choose to stay behind and complete the other ones. So let's just stay behind. But again, for each analysis performed, the platform creates a plot of it. So you have a figure for the data. It also writes out the text for you, so that you have the methodology written, you have the results written, as well as the limitations that the platform can see. For example, if confidence intervals are very wide, that's something that we can objectively measure, right? And that's a limitation. So the platform does all of those things for you. And again, as we said here, no AI is used for any of this. Anything that has to do with data, whether it's analysis of data or writing up of results or anything that is directly or indirectly related to data, cannot be touched by AI based on our risk-based framework. So now I've pushed that results, and now I can now choose to do the same for the other ones. Since I have run this analysis, it now shows as view history because I've already done analysis and pushed it. But for for the second suggestion, overall and stratified prevalence estimates, here the platform suggests that we calculate prevalence of diabetes in the lab as an outcome, any diabetes and self-reported diabetes stratified by these variables. So we can run this analysis. Let's estimate. Okay, so the platform has done analysis. Again, it has calculated the prevalence of diabetes from the lab, diabetes any, and diabetes by self-report overall, and stratified by all the variables that were selected, right? And as usual, you have a plot for it, you have a text, the platform writes out the results for you, and also you have the metadata, which tells you how everything about the analysis, the data set. So the type of analysis was stratified prevalence, the denominator was the entire data sets, and so on and so forth. We didn't apply weighting, so weighting is false here. And again, we can now push these results to our manuscripts. All right, and now the next analysis is, so the hard part of your work is really just the ideation. Once you ideate, everything is simple. It's just a matter of clicking buttons, right? Just click and push. But the hard work that you have to do which no system or automation or AI can or should do for you is that thinking part. You think and say, okay, what's my exposure? Because ultimately that's the value of a study, right? That's where we need human input, where humans can define what constitutes scholarship in terms of creating those relationships clearly defined and ensuring that we're measuring what we're supposed to be measuring. All right. Once you do that, the rest of the remaining research process is pretty simple and things that you can really complete in minutes. Because the remaining is just running the analysis, writing it out. All of those things are completely automated on the Chi-Express platform. You do not necessarily have to do any part of that, right? But your job is to define, the things that matter, which is the relationships, and account for the variables that could distort the epidemiologic relationships. And then here, let's just run this one too. Here's a regression analysis. The platform also suggests other regression. In case you don't want that one, you can explore alternative models. But if you want that one, you can run the analysis. Here we have the analysis loaded up. The outcome is there. These are our predictors. The platform automatically selects reference categories for you. It assumes that you don't know what you're doing, so it helps you out in every single way possible. You can check model optimization techniques here, but in each case, it selects a reference group for you already based on the statistical considerations, right? Statistical power is driven by the in this case, the reference groups want the group with the largest sample size. So the platform does that automatically for you. So in this case, you have the group that is the largest sample size selected automatically as a reference group, but you can change that obviously. So I can choose to say, okay, in this case, while the largest sample size is the 35 to 49 group, I don't want a reference group to be smack in the middle. I want to choose the extremes of age. So maybe the youngest group or the oldest group. So for that reason, I can choose to override the suggestion of the platform and say, well, I don't want the 35 to 49 to my reference group. I actually want this youngest group, right? So it's your paper. You have to make those decisions and say, here I'm going to make a choice. I'm going to change the default to something else that may be more contextually appropriate for the work I'm doing. So again, if I'm fine with the other selections, all you need to do again is click on estimate. Platform runs validation. If there's a problem, it will abort. If it detects a problem in the process, if not, it proceeds with analysis. And again, so here we have analysis done. We have the formatted tables and the unformatted tables. In case, for those who want to suffer, you can grab the unformatted table and format it yourself manually. But in this case, that has already formatted the tables for you. You have the variable, the comparison group. So this was our reference group, 35 to 49, and you have the odds ratios and the p-value. Now, not everybody knows how to interpret research or research findings accurately. So the platform does interpret the results for you in every single time. So here, for example, the interpretation is provided perfectly as required by scientific conventions, right? It also provides the plot for you. Again, for every analysis, you have the results, you have a visualization, and you have the text. And again, all we need to do if we are fine with these results is to push the results to our manuscript and push. All right. Now let's view this document that we've been pushing results to. Let's see what it looks like. So this is the manuscript we created. And this is let's look at let's resolve the variables. The variables that were created that came from analysis, they have to be rendered in a way that is human readable, not just machine readable. So that's what resolve variables means. So it creates that, and then the same thing for the tables and figures that we're pushing. Let's resolve them so they're human readable. So here we have, and then the analysis tray that we're using comes with us in case we want to resume the analysis and finish them in the text editor, as opposed to going back to the analysis. You can run analysis in your text editor as well. But for now, let's just close this for now and look at what we have. So I'm going to make the screen a little bigger, a little smaller, so I can see the whole scope. So these are the results that we've been pushing. Whenever you push a piece of result to the text editor, the platform automatically rearranges the content dynamically. Because remember we said yesterday that we generally perform analysis in 1, 2, 3 fashion. Univariate, bivariate, multivariate, or multivariable, as the case might be. So the platform is aware of that context. It knows that univariate results should come before bivariate results, and bivariate results should come before multivariable results. It also has context for the research question and has a general idea based on that context. It rearranges itself when you push results. So it doesn't matter the order in which you run the analysis. As you push them, the platform will automatically rearrange itself. So as you push content, it crawls its way through the document and situates itself where it ought to be, right? That's why you have different blocks like this. At this point, you have blocks. So once you are done with all the analysis, you can then click here for the platform to automatically clean up a document and reduce the blocks, right? But you can also, I like doing things manually, so I would rather just click here. If you're the manual type, if you like to suffer, for everything we do on the platform, there's an easy way for people who don't like to suffer, but there's also a hard way for people who just like to suffer. All right, I put that in quotes. So if you want to clean up a document manually by yourself, you can either drag and drop, or you select, for example, all of the results and ask for the merge. So the system will then merge all the selected sections into one single unit so that they're not blocks anymore, right? But that means that you'll have to do the merge for the results, and then you have to do the merge for the other parts, the methods, and so on and so forth. So here we have every single thing in one single block now, as opposed to multiple blocks. The same thing with the method. We can simply merge like that. But in this way, the platform allows you to be able to generate your results in a way that is consistent with standard scientific practice. And you don't have to worry about, geez, am I doing the right thing? Because or am I using the wrong statistical test? Because all of that is automated based on scientific conventions and decision trees. And so it's 100% accurate 100% of the times. So the remaining parts of the manuscript I can then generate with the use of AI. So the introduction, the methods, the platform generates with AI. So for example, if I want to generate the introduction, all I need to do is click here, and it opens up this modal, this screen. And there are two ways to generating the content in this case. We have an AI first approach where it says, well, AI, go ahead and generate something for me and I'll edit. And then there's a human first approach, which says, well, let me tell you what I want, and then you can take an edit. The reason we provide both approaches is because we're all different. Some people find it very difficult to ideate, and it's much easier for them to edit the life out of content that already exists as opposed to starting from scratch. And for some people, they like to just start from scratch and have a more customized control over what they're doing. So the platform provides, mechanisms to support both groups of individuals. So if I wanted, for example, to just have AI generate something for me first, all I need to do is just one single click. The platform takes the context of the work, and then it will then create an introduction, which I can then edit as my own and push to my manuscript. So that's what it's doing right now. The other option was to use the human first, where I would select specific boxes, type a few sentence or a sentence or two, and do that for the 3 domains being assessed. And once I'm done, the system creates it. So this is the text that AI has created. We are very careful in providing this text up here, this warning. It says, we recommend using this AI-generated outputs as a starting point and editing it thoroughly to ensure it meets your needs. Any references included may be inaccurate, so use the reference manager on the main platform for valid citations. This content is an initial draft, not the final product, and as the author, you are responsible for the final product. So you can't say, oh, well, it's chi-squares that generated this part for me. No, that makes no sense. that is a clear evasion of your responsibility as an author, right? And so the goal is just to help you marshal your thoughts together and generate content. So if you're ready, you push the manuscript, and the same thing for the methods. The method section of a manuscript is one where people omit very key information. As an analyst, you have to realize that your job is not just generating results, but also making sure that the methods are fine. So to make sure that people have methods that are complete, we have created this kind of form. The premise here is that it's really easier at least for people to fill out the form. Anybody can fill out the form, right? So that's easy. So we've provided the methods as a form where you just select the appropriate answers, and that's it. That's what the methods is, right? So, for example, what was the study design? You say, okay, in this case, it was a cross-sectional study, and that's the end of that answer. What ages were eligible for selection? I can select the ages. I can say these were individuals who were aged these ages. And even if your exact age is not there, just pick the closest one. You can always edit the text later. And once I'm done, I can go to the next question. What was the study setting? Again, the whole idea is to help you, to guide you to providing all the information that is needed for the methods, so that you don't say, oh, okay, I forgot because I didn't know that was important. So in this case, this was a household-based survey. So I'll select that. Then how were participants selected? This was true, for example, a stratified sampling. How were data collected? Maybe face-to-face interviews, if that's the case. Where was the location of the participants? Maybe United States. When did data collection occur? Maybe data collection occurred in 19. I'm just picking up random dates here. I'm not feeling it properly. But the idea is that all you have to do is just select the answers to the question. And once you click on generate methods, that information is just simply passed to AI to just take it and write a method section that includes all of the information we need for the methods. And all you need to do is just push to the section. This part is saying that the AI usage, once you generate content with AI, the platform automatically creates. Let's go down to see that. The AI usage statement, which we can then edit. I'll show you how to edit that in a minute. But we're going to focus on, again, more on this in the next day on how to write. But today we're just trying to show how all of these parts come together in terms of ideating for the manuscript, then creating our analysis plan, and then making sense of it, right? And so, not sure, right? That's how we can then generate our introduction, our methods. But again, keep in mind, our goal as analysts is to make sense of it, right? So, and that starts with creating a very strong analysis plan that reflects the original question that we are trying to answer, and then ensuring that the results and our interpretation of the results make sense. But again, for all the other parts of the manuscript, the same thing. For the discussion as well, we can either have an AI-first approach or a human-first approach. The AI-first approach just says, okay, AI, just take the content that we have and generate a starting point for me based on all the information we have. Now, in this case, it's only possible for me to generate the discussion because I have the results. If I didn't have the results, it will not even allow me to proceed, right? So in some way, there is some dependency built into the process that way, such that, if there are certain prerequisites, they must be present before subsequent ones can be generated. Again, we're going to take some, for tomorrow's session and the next, we're going to just focus more on taking a real world data set with all of its complexity and challenges and going through the process of how do we take the data dictionary, how do we make sense of it, how do we create the variables that we need, and then proceeding with the rest of the process. So that's what we're going to do tomorrow and the next. So the goal is that when you are dealing with your own data sets or your own research questions, then you have a lot of guidance in being able to do that clearly. So here it has written the discussion. And again, same warning. This is just starting point. Of course, it is based on your context. It's not as if it's manufacturing some context. It's based on the results and everything you have. But again, you are strongly encouraged to review it clearly to make sure that it aligns with that. And this is also telling you that the AI usage statement is created automatically as you use AI. Our principle is that AI is not something that should be hidden. It's something, AI is just a tool. So you can always under check here, you can always view AI activity to see where AI has been used and where AI has not been used. So it will tell you which parts AI has been used, and you can disable AI for all of them or for specific sections of a manuscript as you deem appropriate. The tables and figures, you can also move things around by you coming to navigate, and you can move things around from here. You can drag and drop as the case might be if you want to move the order of items and apply changes if that's what you want to do. To cite your work, obviously, scientific documents, we need to provide citations or references. Let me disable this. This section merge is important when you want to allow those check boxes to appear so that you can then select. So if I enable this, it allows me to, for example, select this and merge. And that's convenient in that case. But in every other case, it's extremely inconvenient because it assumes that I want to move things even when I don't. So that button is there to help you to switch it off or on as the case might be. So it takes all right, so you can now switch off that button so that this so it's still trying to merge the sections. All right. So great. So that's merged. Otherwise, if this is on, if you try to copy something, for example, it imagines that you're trying to merge, and that's not very convenient, is it? So that's why you have this button to switch it off, so that now you can just copy things without it assuming that you want to move things around. All right. Citation is also provided for you to cite your work. There's integration with PubMed, so that you don't have to go and start worrying about references from PubMed. You can integrate them directly from the same point into the platform. So here you can search for references from different sources, from PubMed, European PubMed. You can also import references if you have them from another database, and so on. So to search for references, you can type in here, and that goes and searches the PubMed API and pulls the references. Again, our framework is that AI cannot touch anything that has to do with data. That includes references. References obviously are data points, so we can't use AI for that. So to cite a piece of work, you can simply select the ones you're interested in and cite. So before you even search, the platform has already pulled some references that it thinks are very relevant. We don't do a literature review for you because our philosophy is that that's one of the things that are inherently human. The ability to read through a work and add citations to it yourself shows that you accept responsibility for the work. And I do not believe that that's something that should be automated. Of course, automating it is the easy part. That can be automated so easily. But the fact that it can doesn't mean it should, because ultimately that's what shows that you ultimately have read through documents and you are providing statements of citations for statements of fact. So citations are provided, and you can, as citations are added in the text, you also have references added at the bottom correspondingly as well. And this is the AI usage statement that the platform automatically generates. Whenever you have used any AI, the platform generates an AI statement and adds it to the end of the document to show that, in this case, it says that AI was used to, this research utilized AI tools on the Chi-Square's platform for light copy editing, specifically for grammar and style enhancements, content suggestion, and text reformulation. All AI-generated content was reviewed and refined by the researchers, who take full responsibility for its accuracy and integrity. The chi-squares platform does not employ AI for data analysis, reference management, writing of the results, interpreting the results, or anything that has to do with data. But for all the other parts that involve data, yes, that do not involve data and where AI is used, it's your responsibility as author to make sure that everything is kosher. All right, so that is it for today. I'm going to stop there and see if there are questions so that we'll have enough time to answer any questions people might have.
Thank you very much, Prof. They were asking about yesterday's homework, if you're going to go through it.
Yes, definitely. I want to do so after your questions.
Okay. Okay, so thanks, everyone. If you have any questions, please post them in the chat box. And if you want to speak, okay, Micah, you can go first. We're also sharing the attendance register on the chat box. Please look out for it and kindly complete it so you can get your certificate sometime soon. Micah?
Okay, thank you so much, Lungile, and thank you so much, Prof, for having organized such a crucial and a good presentation. Actually, for me, I just have one question regarding the data management aspect, because right from the start, we started from all those stuffs, like we used that HIPAA principle, FAIR principle, all that. Now today was about handling data, but I haven't seen where maybe you are handling kind of a missing data or the not applicable data, so the one with the NS. So I wanted to know how shall we handle that, or maybe any technique to handle the missing data, or kind of the not applicable ones that those which have NS, you know that, because
Yeah.
I've seen your skin on your analysis, there was somewhere on your analysis you will see missing values. So I can see even now here there is like 3622, another one 471. So I don't know how can we go about that aspect, because unless if we will restart this stuff to get another time tomorrow before we engage more on it. That's my only question. Thank you.
All right, that's a very good question. So let's answer that question. So handling of missing values is a very, very serious thing. The way the way some especially some online tools allow you to handle missing data are going to cost you more damage than good. Because for us to handle missing data, we have to understand, first of all, why the data are missing, right? There are three mechanisms through which data are missing. And the idea that we can somehow, for example, impute data, the two most common approaches people will use will be things like multiple imputation, which is like, okay, we are doing a very educated guess to replace that missing value with what we think it looks like based on what the other, it's like, okay, if it looks like a cow or smells like a cow, then it's a cow, right? Well, the problem with that is that there are very heroic assumptions for things like multiple imputation or even inverse proportionality weighting. It assumes that data are missing, at random, right? Now, that is a very heroic assumption because it's almost impossible for us to test that from the data, right? If the data do not miss that specification, if, for example, data are missing not at random, MNA, pattern of missingness, and we use, for example, multiple imputation or we use inverse proportionality weighting, then we are causing more harm than had we left the missing values the way they were. Now, the problem with this is that a big challenge is that it is impossible for us to disprove MNA save with there's no statistical tests for it. So it's not something we can run an algorithm and say, oh, this data are missing so and so way, right? We can't tell. Only the investigator can actually tell based on context what the pattern is. So that makes it very hard to automate it. That's why it's not automated. Now the question is, How do we deal with that? Now, if I have a variable, let's pick a variable here that has missing values. Let's say that my variable is let's say, education. It has 4,413 missing values. Now, first of all, I need to ask myself, why are those values missing? Well, in this case, the values are missing. Let me see. Let's explore that. So the first thing I have to ask myself is, why are those responses missing? Are they missing because, for example, maybe the study included people who are aged 0 to 80 years, but only persons who, for example, had a particular age group had information for education, or those are different reasons for which data could be missing. Now, let's say that my study population was one fixed denominator and there was no such exclusion, skip patterns. If I want to make sure that these individuals are not excluded from analysis, because when you do regression, it does listwise deletion where individuals with missing values are removed. One way to handle that is to say, well, since I don't want the missing values to be excluded, I'm going to just set this as a valid category. So I can now call this missing group. Now, what that does is that it changes the spirit or the form. That's no longer missing, right? It's just like another group. I can call it indeterminate. I can call it unknown, right? But suddenly, I no longer have 4,413 missing observations. 4,413 missing observations in my data, right? So that is one way you can handle it. Now, this will only apply, obviously, if the responses are the predictor variables. If I have a variable that is binary, 0 and 1, I can't just create a third category because now it's no longer binary, right? It's now has 3 categories. So one option for you is to just treat the variables as, as a valid category. That way, if they're predictors, then you have a separate category that is for individuals who have missing values, and then that solves the problem. You can also choose to move this category into another group, right? And maybe you have some hypothesis that individuals who have missing observations are likely to be related to that group for whatever reason, right? So the platform provides you some basic tools to handle that, to either treat the missing groups as a valid group, to merge in that group. But in terms of things like multiple imputation or things like inverse proportionality weighting, we have intentionally not included those techniques because most times, if you provide something for people, they're going to abuse it. They will just use it, right? Whether or not it fits the context. And so, but in the future, that's something we're trying to, one of the approaches we're trying to solve the problem is to say, we will provide you with the tools for multiple imputation and for inverse proportionality weighting, but we're going to force you to challenge the assumptions that are required for that procedure. So when you say, okay, I want to use multiple imputation, the platform will force you to walk through a series of steps to test whether or not the assumptions are met or not met. That way, people who want to do multiple imputation can still do it. But for now, we have intentionally not provided that because of the tendency for abuse of handling of missing values, which in most cases creates more problem than solves them. Sorry, that's a very long-winded explanation, but I hope that makes sense to you.
Thank you. Okay, any other questions that I might have missed? Please post. If you posted it earlier, I might have missed it because there's a lot going on there, the chat box. Okay. Daniel?
Right. Thank you so much. And thanks for really brilliant discussion on this very wonderful platform. Yeah, I had a similar question to what was asked on multiple imputation, but yeah, you've really well addressed that. But on the analysis methodology, especially for the regression, I had asked in the chat and somebody responded, but I wanted to follow up.
about multi-level modeling. Yeah, if you want to include some random effects in your model, does the platform allow that? Because I think you didn't go to that level yet. Thanks.
Yeah, so we've provided a lot of different types of models. Some of the things that some of the models that we are trying to address in the near future are, things like mixed effects modeling and, hierarchical models, which allude to the issues you're addressing. For now, they're not part of a release that we have provided. However, we allow for mechanisms to provide, the platform allows for other mechanisms to account for random effects. For example, you can set as a cluster, for example, because the whole idea is that you want to reduce the variation from that are not necessarily part of the explanation of the intervention, right? So, but in the near future, one of the things one of the things on the pipeline are some of those models explicitly. Models for hierarchical modeling, those for mixed effects, and then those for survival analysis, and also conditional logistic regression as well. Those 4 are part of our planned release in the next few weeks.
Thank you. Okay. Okay. Any other questions?
But for now, to find the regression models currently supported, you just simply go to estimate, come to regression, and you can see these are the ones that are currently supported. And we're trying to use Pareto principle here, and the 80-20 principle, that this cover 80% of needs, and then we can then provide increasingly more advanced models as time goes on.
There's a question. Can the platform link or extract references from EndNote?
Can it do what? Sorry, I didn't hear the
Can the platform link or extract references from EndNote software?
Yes, you can export your references from EndNote, and then when you export the references, you can then import them in your library in Chi-Squares. So yes, you can do that, but it's a 2-step process. You export from there, and then you import the references into your citation library within Chi-Squares. So yes.
Momodebe, Philip, your question is incomplete. Hello, Prof. I noticed that on the Chi-Squares platform, I'm not allowed to design a survey. The system asked me to upgrade. Is the platform still free of charge? I've switched to version 2.
Well, it's a premium model where you can do certain things under a free plan, but if you wish to use the more advanced features, then you have to get into a paid plan.
Hello. Am I audible?
Yes, you're audible. We can hear you clearly, yes.
Yeah, thank you. Thank you, sir, for the wonderful session. Actually, I couldn't attend yesterday's one. Is there any recordings available?
Yes, there is. On our YouTube channel, which will be shared with you.
Okay, and one more thing, I think all the kind of research services are available in this web platform, right? Like if Mendeley is for referencing only, or that Zotero, that apart from that, all the kind of things are available here. Is that correct?
That is correct. And like I said, if you wish to, if you have, the platform has an inbuilt citation manager or library. So if you have been using, for example, Zotero, you can still export your references from Zotero or EndNote or whichever, and you come to import. And you can then import you can then upload the references that you've exported from RefWorks or EndNote or whichever into the platform, and the platform will read it accordingly. And then it goes into your citation library.
Okay, thank you.
I hope that makes sense.
So if I want to perform multiple regression, I will select all the one active on the chi-squares platform.
So I didn't get a question. If you want to perform multiple regression, you do what?
Select all the ones active on the chi-squares platform.
All the ones active.
Mm-hmm.
Well, yeah. So if you want to perform regression, yes, you'll have to use. I'm trying to answer the question as best as I can, or as best as I understand it. So if you want to perform a regression, yes, you can select one of the ones that this have been carefully selected to capture the most of the regressions that you would perform in 80% of scenarios. Now, if you want to perform something else that is not yet supported, well, then that means you can't do it on the chi-squares platform.
Thanks, Prof. Please, when will we have sessions for qualitative studies? If I remember well, Prof indicated that the platform can equally deal with qualitative data during its launch. Any clarification, please?
So you can collect qualitative data in the survey platform. So the survey platform is designed, the platform is this is an ecosystem that supports data collection and all of that. So when you're designing your surveys, you can indeed collect qualitative data, but in terms of the analysis, the analysis engine is optimized for quantitative research. So data collection, you can collect any kind of data, including qualitative, and indeed we have some rudimentary ways of analyzing that. But for this analysis module, its focus is on quantitative research.
Thank you. Okay. Doris. Doris, you're not audible.
For the opportunity. I'm grateful for the lecture today. Please, my question is, I just saw the call early hours of the morning on one of our platforms, and I registered this morning. Now I'm asking, is it possible for me to have access to the lecture for yesterday and possibly today's one also, so that I can follow better?
Yes, that will be shared. Our YouTube links will be shared.
Okay.
My colleague has already responded to your message, Doris.
Or
Can just check.
immediately after the message, I got cut off by the network. I just joined again.
Okay, we'll share it again. We'll share it again just now.
I'm
Thanks.
grateful.
You're welcome. Will we be delving will we be delving to linear and multiple regression as well, or can we use the platform to practice on our own?
You can use this is just supposed to be a model for you to then follow. But the same principles, so we can't possibly go through every single procedure on the platform, but this just sets principles so that you can then follow for other work. So we will not be necessarily going to every single one, but you can follow the same principle. If you go through the analysis suggester, it will tell you whether it's a linear regression you need or whether it's a Poisson regression you need based on the variable type, but the flow is exactly still the same every single time.
Thanks, Prof. Thank you for creating such plates. When we use the manuscript created from this platform, will there be any issues like bias or AI automation? Which part needs correction or plagiarism issues before we use? Can methods and results be copied as shown by the platform?
Yeah, so like I said, when you go to the manuscript part, let me go back to I wanted to go to the analysis. Well, let me just open a new tab here. So everything that has to do with analysis and the methods has no involvement with AI. Now, for the introduction and all of that, you can choose not to use AI. You're not required to use AI, right? So you can choose not to use AI. You can choose to go into a document and just type things yourself. So I can just come here and manually type, right? You always have that choice. You can also choose to go to the settings and go to AI controls and switch all AI off. So, and then you do things manually that way. So you have all of those options available to you.
What are advanced features that are not free on the platform? But we've already shared the link with you, Beauty, the pricing link. If you can check one of the messages we responded to. Josiah has just shared it again. Thanks, Josiah. Okay, I don't think we have any more questions. Okay, someone just raised their hand. Where is it? Okay.
Bismarck.
Yes,
Hello.
Bismarck.
Yes, please. Good evening, and thank you, lecturer, for your explicit details and information you are giving to us here. Please, my question is just simple. We've had a lights out, and due to heavy rainfalls over here, and our network is not all that stable. Yesterday class I joined, but today our network is not stable on our side, and I don't know if I can still be able to submit my yesterday's assignment, and likewise today what will be shared again.
Yes, you can.
All right, thank you.
Okay, I think that's all. So we have time now, so we'll do the homework tomorrow. That would encompass the assigned work for the past 2 days, so that we don't go over time. So we're going to stop here. And the homework for today is already on the document, but we're going to post it again. So again, you can share it once you've completed it on the same channels as you were recommended. But in the absence of any other thing, we'll see you in class tomorrow. Thank you very much.
Thank you very much, Prof. Well done.
Thanks, yeah. Mungile, I always
Thank
have
you very much, Israel.
Is that KP?
No, Regan.
Oh,
Again.
how are you? Hey, how are you? You sound
Yes,
like KP. All right. All right. Thanks so much.
I'm connected with my tablets because it has any battery on my computer.
Okay. Okay.
That's why I have this name, Stanley Research Unite.
Okay. Awesome. All right. Thanks so much. See you guys soon.
Okay.
Bye-bye.
Many thanks to you.
Thank you. Cheers. Bye.
Hello, Dr. Anoja.
Yes. Hi, Longile.
How are you doing today?
I'm doing fine. No problem.